Today, I will demonstrate a technology we call Super-QAM, which can significantly increase speeds and lower energy usage. Some recent exciting news is that 3GPP approved greener networks as part of 5G Release 18. This opens a great opportunity for Super-QAM and other technologies to make 5G a greener network. Let's first have a quick look at how Super-QAM works. The key concept is to reduce the noise in the receiver in an iterative fashion to incrementally improve the signal quality. The iteration cycle goes through 3 steps. First, reducing the phase noise, then addressing nonlinearities from the power amplifier, and finally, rectifying IQ imbalances. This iterative cycle is performed in 2 phases. First, on the reference signal to achieve a clean channel estimation, and then on the data itself to achieve the best possible signal quality. With improved signal quality, we can utilize higher order modulation, which improves throughput speeds. If we can improve the signal quality so we can use 1024 QAM, then the throughput speed increases. And as we increase the order of the modulation, the throughput speed keeps increasing and increasing. When we reach 16K QAM, we have boosted the throughput speed with 75% from where we started. In our first demo, I will show our non-real-time setup that is operating in sub-7 GHz spectrum band. The setup is comprised of an FPGA board which is used to transmit predefined signals through 8 channels. Each channel has a base station power amplifier preceded by a controlled attenuator and a preamp stage. A realistic fading channel for each path is then emulated by an 8x8 channel emulator. Finally, the received signal is captured by a set of UXR scopes. Here we see the spectrum of the transmitted signal. And when increasing the signal transmit power, we can see the nonlinearity floor going up. Let's see how Super-QAM can clean up a noisy 16K QAM signal. Since 16K QAM has so many points, we have to zoom in to see what happened. In the top left corner, we see how the signal looked like before we started. If we look at the subsequent plots, we can see how Super-QAM is able to significantly improve the signal quality. We repeat this testing for different transmit powers, and in this diagram, we can see how Super-QAM allows proper decoding of 16K QAM. In our second demo, I will show you our mmWave setup which we are running over the air in real time. Here you can see our anechoic chamber where we set up a transmitter chain, creating a test signal using 2 layers, which are transmitted using an RF head with 64 antenna elements per layer. To model different levels of signal qualities, we apply different levels of transmit gain. On the receiver side, we are using our mobile test device with Snapdragon X50 5G modem RF system that can perform the Super-QAM technology in real time. On the spectrum analyzer, we can see the spectrum of the transmitted signal, and when we increase the transmit power, we can see the nonlinearity floor going up. Here you can see our real-time demo interface where we can adjust different parameters like number of iterations. We can also see the performance in terms of block error rate, error vector magnitude, ACLR, and the throughput speed. As you can see, before Super-QAM is applied, we have inadequate performance with block error rate of 100% and error vector magnitude worse than -30 dB. Now let's see what happens if we apply Super-QAM. On this plot, we can see how the 1K QAM constellation looks like after each iteration. On the top left, we see how it looked before we started. The next one shows after we apply 1 digital post-distortion iteration, and then another one combined with phase noise correction, followed by 3 more phase noise correction iterations. As you can see, the signal is much improved compared to when we started, and the error vector magnitude is reduced to -38 dB, which allows for proper decoding of 1K QAM with low error rates. As you can see, the measured throughput is 1.3 gigabit per second over 100 MHz channel, or about 10 gigabit per second over a more typical 800 MHz channel. This represents a 66% gain over today's 64 QAM. In this demonstration, we have seen how our Super-QAM technology can improve the signal quality to support higher order modulation. In our sub-7 GHz lab setup, we were able to support a revolutionary 16K QAM. And in our mmWave over-the-air setup running in real time, we demonstrated 1K QAM. With Super-QAM, we can both significantly boost data speeds and reduce energy utilization for greener networks.